All right, so we're back, and we've talked about life as a low mass star and how we end in that planetary nebula explosion. Again, it's poorly named, but what are you going to do? But now we're going to look at high mass stars. Remember, these are our, you know, burn bright quickly and fade out friends. So they only live a short time, but their lives are fairly violent and can be spectacular. So let's see what we mean by that. So a lot of the stuff we looked at for a high mass star or for a low mass star is actually going to be true for a high mass star, except that they're going to have a few more sequences in between. And when they become giants, they can become supergiants and hypergiants. And they end in this much bigger explosion, which is called a supernova. And high mass stars don't leave white dwarfs behind. They leave either neutron stars or black holes. All right, so we'll probably start to cover that next week. It's about the right time to cover that. Yeah. Okay. So you'll notice that if you remember when we talked about low mass stars, the whole problem was there wasn't enough mass to overcome the degeneracy pressure in the carbon cores. But with high mass stars, you can almost say that a high mass star is a star that is defined such that it has enough mass to overcome that limit, right? There's enough mass that it can still get hotter and get carbon to start fusing. So that's the difference between a high mass and a low mass star. If you're low mass, you just don't have, even as big as you are, and our sun is a pretty big low mass star, you're not ever going to get carbon fusion going on in our star. But if you're big enough to have carbon fusion, you start to build all these other elements like nitrogen and carbon and oxygen, and you start to get all of these this fusion cycle to go. The core temperatures allow all these elements to be created to absorb either heliums themselves or hydrogens themselves or both simultaneously, and that's where you get all this type of stuff going on. All right. Now, in the late stages of a high mass star, similar to those of a low mass star, right? So hydrogen core fusion is still in the main sequence. Then you have these shell fusions to become giants and supergiants, but you're going to have more. Okay, and in high mass stars, you get oxygen, neons, and magnesium, all the way up to iron. All right, and you'll notice here you can sort of get everything all the way up to the last one we saw was magnesium here, and you can continue to go up from silicon to sulfur to chlorine, all the way to manganese, all the way to iron. All right. So now this is rather an interesting point here. There's a subtle point. So the Big Bang, so the atoms, the way of creating atoms is fairly interesting. So the Big Bang, the moment all of existence was created, or observable existence rather, 75% of hydrogen and 25%, it was 75% hydrogen, 25% helium. And since then, anything heavier than hydrogen and helium have all been created through some star process. All right? Some of them more spectacular than we'll even teach in this, well, than your book will even say. So for instance, it was shown recently, like to get these, what we'll find is that in stellar evolution you get iron, and then everything heavier than iron you get in sort of supernova explosions or exotic collisions. When I mean exotic collisions, there was a neutron star collision that was observed in a galaxy far away recently that was able to create large Earth size, like Earth mass, like the size of the planet, of a lot of these heavier elements, including most notably a chunk of gold that was as massive as the Earth. So heavier elements are created in truly spectacular fashion. And we'll discuss more of this as we go along, sort of as we recap. But you can see iron is right here at 26, and this is where the fusion process ends. Or it's not where it ends, it's where it stops yielding energy. To fuse more, you need to add energy, and then you can use that additional energy to create heavier elements, but you don't get anything out. So we'll see that in detail. So we can see that helium makes carbon in these low mass stars. And for those of you who don't know or who have not seen it, this is a periodic table of the elements, and it's organized in a pretty interesting way. It's organized by shell electrons. It might not seem like much, right? Because it goes 1, 2, and then 3, 4, and there's these spaces. But it's actually organized in a very clever way based on the number of electrons and protons you have and the number of electrons in shells. So each of these groups have things in common, like the number of valence electrons available to them and other such things, and other certain properties. So it's a nice way of sort of getting atomic data in one one nice little compact table. But we can see that that helium fusion will make carbon in low mass stars, and the CNO cycle, which takes place in high mass stars, that gets us beyond carbon, right, to our nitrogen and oxygen. And then we can see some of the other elements form and start to take advantage of those very, very high temperatures that occur with the contraction of a massive core. All right. So we can see it builds up. Now they're showing the advanced nuclear burning, right? Carbons and oxygens can form silicons, and then oxygen and oxygen can form sulfur, and then you get silicon and silicon forming iron, all right? And iron is, if the core temperatures in stars with greater than, so if you're greater than about 8 solar masses, that allows iron to form. And that's when you get the really big explosions. All right, so we can see that going on there. And you'll notice that basically, much like a low mass star, you have shell burning, but in advanced nuclear burning proceeds, you get a series of nested shells. So notice you have an iron core here, and then you have silicon fusion. You have a fusion of oxygen, neon, and magnesium. Here you have carbon, helium, hydrogen. But keep in note that the iron is inert. All right, you have to add a tremendous amount of extra energy externally to happen. There's not enough heat. You can't heat up the system to have that happen. You run out of the degeneracy pressure locks it in. So you run out of heat energy. You can't heat up. You're just sort of stuck there at iron. And in order to get iron to fuse, you have to add energy to the system. The only process known that can do that is that supernova explosion we'll talk about at the end. You get a whole lot of collapse down into this core. That adds energy, and then it explodes and rebounds out, and heavier elements can be exploded out from the supernova. So as you can see, you get your advanced shell burning. And you can see here, this is an interesting table. So this is what I was talking about hydrogen to helium being the most energetic fusion reaction. You can notice you get other reactions, but you need a whole lot of temperature and you get diminishing returns. All right, and you'll notice that iron, you don't release energy anymore. So after iron, it takes energy to fuse into these heavier elements, but you do get energy from fission, right? If you remember fission, that's when you have one giant nucleus split off into 2 smaller nuclei, right? So that's a fission reaction will release energy on that end. All right, and yeah, you'll also notice that. Well, we're not at that slide yet. That's okay. So going forward, you'll also notice that there's a larger abundance of even number. So hydrogen is an odd number, but you have helium. Then you'll notice there's very little lithium, right? But then you get to, and there's very few of these. Maybe that's why I don't like to get beryllium, these sort of low numbered elements. But you'll notice we get to carbon, we get a dip, and then we get to oxygen, we get a dip for the odd numbered, and then we get neon, a dip. So you'll notice that the abundance of even molecules, or with an even number of protons, is evidence for there being that helium capture is the main mechanism in a lot of these fusion, large mass and even low mass fusion events in stars. All right. So we see that there. Okay. And again, we can look at those elements by just looking at the spectrogram of stars or of the universe or gas clouds in the universe. We can use spectroscopy to look at what any gas cloud or star is made of, and the relative intensities of the spectra will tell us what the dominant elements are. All right, so now we want to look into how does a high mass star die. And you'll notice this looks like a planetary nebula, but it is much more violent. And this is actually the remnants of a supernova explosion. So basically, the supernova occurs just like I told you. You get all of these shell layers and this inert iron core. They collapse into the core collapses, and that rebound shock wave creates the supernova. Okay. In a supernova explosion, the collapsing core and shells drive all the electrons into protons, and out you get neutrinos and neutrons. I don't have my pointer on here. You get neutrinos and neutrons. All right. So basically, what's left over is not a white dwarf. A white dwarf is bound by electron degeneracy pressure, but there's enough mass to drive the electron into the proton and create just a big ball of neutrons, and the neutrinos will be able to escape. And we can actually characterize neutron stars by looking at, we can see the neutrinos, the stream of neutrinos from these stars. So neutrons will collapse to the center, forming what is called a neutron star. And a neutron star is some of the densest material you will ever see, but we will talk about that in detail in the next chapter. Okay. So energy and neutrons released in a supernova explosion enable anything heavier than iron to form, all right, including gold. So again, there's a few things this is a time to take a little bit of a step back. So there's a saying in popular culture that we're all made out of star stuff. And well, you're mostly hydrogen and oxygen, you're mostly water. So your hydrogen is either star stuff or hydrogen from the Big Bang, which may be an even cooler origin story than stars. All the heavier elements in your body, carbon, which you need to run your organic processes, the oxygen you breathe, all of those atoms, the only known way to create those is in stars. So it is correct to say that you are made of star stuff. Now, what I find more fascinating is for those of you who have gold jewelry or silverware, or anything you can think of that has a heavy metal, titanium, something like that, what's interesting there is that all those elements had to be created in at least a supernova explosion or an explosion greater. So like I said, the two known processes, there's now something besides a supernova, which is a neutron star collision, which is even more spectacular than a supernova. But a supernova, the gold that you look at was created in something of that, in an explosion of that kind of power. So in either a dying star, right at its very last seconds of existence, and supernovas do not take long. They happen on the order of minutes when they happen. So for stars, that's almost instantaneous. And yeah, so either that or energetic collisions between neutron stars or neutron stars and black holes. So exotic collisions create all the heavier elements we see in the universe. So it's pretty interesting that the atoms in the metals that you use frequently have a very interesting origin story. All right, and they have traveled, and it's very accurate to say that they are and you are made out of the processes of stars. So that's where he started. Pretty neat, huh? So let's see here. So, of course, the supernova we're looking at here is the Crab Nebula. This was seen in 1054, and you can actually see it with a good telescope. The energy released by the collapse of the core drives the layers into outer space. So this is supernovas are a huge driver of gases and heavy elements into the interstellar medium. And in fact, you can tell old stars from young stars, right? If you're looking, because particularly back in time, you know, because when you see galaxies farther away, you can tell a star is relatively, or even an older star today is from the young universe, if you will, based on the amount of heavy metals and heavier elements it has in it. Older stars tend to be mostly hydrogen and helium, with very few other elements in them. Whereas a star like ours, our star is like a fifth or sixth generation star or something like that. I don't know off the top of my head, but I do know that we don't just have hydrogen and helium floating around, as evidenced by our Earth, right? We're here, there are not a lot of heavy metals, but we have them. And that density of heavy metals is pretty uniform throughout the solar system. So that is the Crab Nebula. And most of the supernovas we see are from faraway galaxies, all right? So you'll notice the closest supernova of the last 4 centuries was seen in 1987. And so you'll notice here there's a star, and then we very quickly, this is in visible light, you see a bright patch, all right? So that is very much, you can see sort of this triangulum, see everything right there. And so that supernova is very bright and comes from deep space. Supernovas are usually so bright and release so much energy that they outshine their host galaxies very briefly. And keep in mind that the luminosity of the galaxy comes from billions to tens of billions of stars. So a supernova explosion is pretty impressive. All right. So what we can see here is that basically a star's mass will determine its entire life story, all right? Because it determines its maximum allowable core temperature, right? The heavier the star, the more you can fight that degeneracy pressure, the more temperature you can raise in your core, the more fusion layers you can have, all right? And if you can get above a carbon layer, you will go supernova, okay? High mass stars, they burn bright but die short. You know, they have short lives, eventually becoming hot enough to make iron and end in supernova explosions. Low mass stars have long lives and they never become hot enough to fuse carbon nuclei and end as white dwarfs, okay? So we have here the summary of the stages of life of a low mass star. That's something to look at. And you can see the same thing for life as a high mass star. I'll let you kind of look at that on your own. And we should be ready. Oh no, I always end this prematurely. So we've learned about lifetimes of stars, but now that we know about low mass and high mass stars, if you recall last week, we talked about stars in binary pairs, and that binary pairs were common. That's a system of 2 stars orbiting each other. And so we're going to talk about what that looks like and some of the interesting interplays that can happen in stars that have in systems that have 2 stars. So let's take a look at some pictures. So we can see here these are obviously artist pictures. These aren't real, but they make the they're created from observation. What I mean is that they're indicative of things we can observe and conclude from observations. And you'll notice here that we have Algol and its partner star, all right? And Algol shortly after its birth. The higher mass star on the left evolves more quickly and lives through more of its life than its low mass companion star, right? So before, this, believe it or not, will actually be Algol. This was its heavy mass companion. But as its mass as it got big and went through its stages, well, the binary relationship allowed something interesting to happen. It allowed mass to be siphoned off from the high mass star to the low mass star. And now you siphoned off enough so that you reach an equilibrium that you sort of have this low mass star, and this high mass star has now become a low mass star sort of at the end of its life. And now you have a high mass companion that's increased in mass that's during its main sequence. So you've shortened the life of this partner, and you've elongated the whole process of this one. Okay, and so that's the interesting dynamic that can happen with binaries, is they can exchange mass. And essentially what we have is that the stars have changed which one is the high mass and which one is the low mass star. So some interesting stuff. The binary star Algol consists of a 3.7 solar mass main sequence star and a 0.8 mass subgiant star. So that tells us that because it's in its subgiant phase, it already used up all its helium or its hydrogen to turn into helium. Okay, so it's already used up its core stuff, then it started transferring mass. All right, so what's strange about the pairing is that the main sequence star is the heavier star and the dying star is the lighter star. And the only explanation is that mass was transferred. Okay? We already talked about that. Okay, so now we want to continue our discussion of stars. We'll go into the next chapter. All right, moving on. I'm trying to see. Yeah, we do have a Monday. We have Memorial Day. That might make things interesting. Okay. But we're actually in. What I might do is I might, because we did take a Monday off, I may just do a taped lecture for you to watch at your own leisure. I may talk about galaxies and just do a screen captured lecture, but we'll decide that. I'll talk about that more after class. I'll think about that. But I might just post it on, like I might just put it in a room and record the lecture, and then you can come watch the video. Files. That's what we need to do. All right. All right. So we look at our we finish off stars by talking about white dwarfs or dead or stellar corpses. All right. So that will be white dwarfs, neutron stars, and black holes. Okay. So let's look into. We sort of defined a white dwarf before, but let's look at some of its details and see not only what a white, explore more what a white dwarf is, but we're also going to see what happens to a white dwarf when it's in a close binary star system. Okay? So, a white dwarf, as we saw, is the burnt out husk of a low mass star. All right? And we can see them in they're relatively dim in ultraviolet and X-rays, while Sirius B, its brothers, outshines both. Okay, Sirius is seen by the X-ray telescope. What's it going to tell me here? All right, so white dwarfs are the ruining cores of dead stars, and electron degeneracy supports them against gravity. So I'm not sure which one is the white dwarf here, because I think the white dwarf is supposed to be, because they can have high temperatures, so it's not clear where it will be. Sirius B. No, it doesn't really say. That's fine. We already went through this before, right? We saw how the white dwarf happens. So white dwarfs as objects are much smaller than stars. They have about the mass of a star, right? But you'll notice that a white dwarf mass, solar mass, is about the size of Earth. All right. Now keep in mind that you can fit 1 million Earths into the sun. All right, so you're taking away the volume, you're decreasing the volume by a factor of 1,000,000, and you have all the mass in there. So white dwarfs are very dense, and something interesting happens to them, which is that as their mass goes up, so if you have more of a white dwarf, right, if you have more mass, that means you have more chairs. That means your pressure increases and pushes down, right? Your degeneracy pressure is holding in, and you become smaller, all right? And if you remember, I told you to keep an eye on this whatchamacallit, the Heisenberg uncertainty principle. Right? So as our mass goes up, delta x is going to go down. And that means delta p increases. But delta p can't increase forever, right? Delta p max occurs, implies that v equals c, not infinity, right? So we're going to find that there's actually a white dwarf mass limit. That quantum mechanics predicts that there is a mass at which the electrons would be moving at nearly the speed of light. And if you exceed that, and it should be impossible to exceed that mass. So we just talked about this part with the quantum mechanics, that the particles move faster as they're squeezed into very small space. So as the white dwarf approaches this mass here, 1.4 solar masses, then that velocity we talked about earlier becomes equal to the speed of light, and we don't understand quite yet the statement that objects don't move faster than the speed of light, but we will see that it takes an infinite amount of energy. It is not possible to accelerate objects at the speed of light. And because nothing can move faster than light, a white dwarf cannot be more massive than 1.4 solar masses, and this is known as the white dwarf limit, also known more technically as the Chandrasekhar limit, all right, of a white dwarf. Okay, now how black holes and neutron stars were discovered is you would think that if everything ended in a white dwarf, you would never find white dwarf or companions where they were orbiting a small compact object whose mass exceeded 1.4 solar masses. But we do. And remember, you can use Kepler's law to easily get the mass, and at least outside the, way above the error bars of 1.4, of 0.1 solar masses or whatever it is. So we see that they exist, and then we have to understand how they can exist. And the conclusion we arrive at is they're not white dwarfs. All right? So in a binary, a white dwarf itself can start siphoning off mass from its partner. All right? Now what happens there is you create this disk, and you start adding a little bit of mass to that you can either add, you can heat up or add mass to the neutron star. And if you add mass to the neutron star, you make it smaller. For the most part, you get a very hot, what they call accretion disk, similar to the accretion disk we talked about when stars form, but this will heat up, and when it gets to a certain point, it will spike and flare. All right? So we just sort of summarized what we did last chapter and got to this part, to the accretion disk. Now we really want to know what happens next. So friction between the orbiting rings of this disk here transfers angular momentum outward and causes the disk to heat up and glow. And then the temperature of the accreted matter eventually becomes hot enough for hydrogen fusion, and that becomes interesting, right? Then all of a sudden it starts to look like a star. But we still have an inert core here. But we sort of get this shell fusion, and this creates a flash known as a nova. Okay? So the terms nova and supernova were actually not to describe the ends of stars, which might have made more sense, but were actually first observed in these white dwarf binaries. And that's why a nova, does the siphon process happen because of attraction? No, absolutely. Attraction's right. They're two gravitational masses, and the energy is free to float. And so basically, two massive objects like this, unlike our own star, in our solar system, the center of mass is at the sun, right? But for something like this, the center of mass is outside of both of these. So they both orbit around each other. And because of that, the mass and gases and stuff will want to flow towards, will be attracted to each other in this way, and they'll be able to exchange. All right, there'll be an exchange of the outer layers being more gravitationally attracted than the inner layers. All right, and that's where the exchange happens. So basically, supernova were first a property of white dwarf binaries, and then it was seen that that massive stars, when they died, they were thought to also be the same process, but then they were able to be, because they looked the same at first, but then they were actually able to tell the difference between the white dwarf supernova, which we'll talk about soon, and a massive star supernova. And in fact, that's one of the most important parts of measuring the large structure of the cosmos, is being able to tell the difference between those two types of supernovae. So when we look here, we have fusion starting in this disk, and that creates a nova. Now, if the white dwarf, we'll talk about that. We're not done with the nova, but we can see a picture of a nova here, and the nova star system temporarily appears much brighter, and the explosion will drive out that accreted matter out in space, and so it has to start the accretion disk process again. However, if the white dwarf, when it accretes, has enough matter to reach this white dwarf limit, you're going to get a complete explosion of the star. So a white dwarf supernova, we already covered the massive star supernova with iron cores and all that good stuff, but carbon fusion suddenly begins as the white dwarf in the close binary system reaches the white dwarf limit, causing a total and complete explosion of the white dwarf. Nothing is left behind. It's completely vaporized and destroyed. And this is called a white dwarf supernova. And again, I told you, we have two types of supernova, and while massive stars can be variable and give us varying degrees of brightness for the supernova, the white dwarf supernova is interesting because it can only happen if the white dwarf is at the Chandrasekhar limit. It's at that 1.4 solar masses. And because of that, we know because we know the mass, and we know how we can figure out fairly precisely how much energy would be released in the complete obliteration of that star. And because we can tell these white dwarf supernovas from other novas, that gives us a standard to apply through the farthest reaches of the universe, right? So if we look at the characteristics over time of a white dwarf supernova, we can actually then know its distance, because now in that equation we have the apparent brightness, but we also have the total power. And so from there we can calculate the very longest distances in the universe. Okay, and that's pretty cool. And we'll see that here, and we'll see the difference between the two in this graph. So you can see this is the luminosity profile over a year. So it's not a quick blink and you miss it phenomenon. You can look at how a massive star supernova, and it has this bump, how it behaves over time, and you can see the intensity profile of the white dwarf supernova also over time. All right, and so you can tell qualitatively which one is which by yourselves. You can say this one is a massive, it has a lump, and another, it has these kinks in it. This is a massive star supernova. You can see here that the luminosity becomes bigger for the white dwarf supernova, but then once it sort of linearizes straight out, it stays as a straight line, and that will be your white dwarf supernova. And so because you know the white dwarf supernova, you can measure the brightness in the lab, right? And then you know how much power it must have, because all white dwarf supernovas have to ignite with the same exact power. You can calculate distances out to about the universe when it was 1 billion years old. All right? Pretty cool. Pretty good stuff. Okay. So supernovae are much, much more luminous, even they say much twice, than novae, about 10 million times. The nova is really more like temporary shell fusion layer, and it leaves the white dwarf intact. The supernova completely obliterates the white dwarf, leaving nothing behind. All right. And of course, we saw that the light curves differ, but what we didn't see is that the spectra differ, right? Exploding white dwarfs don't have hydrogen absorption lines, so we can look at them and tell very clearly which one is which. And again, that makes measuring very long distances in the universe accessible. Okay. So any questions about white dwarfs before we move on to neutron stars? Okay. All right. So now we get into sort of our more exotic stellar corpses. So the neutron star occurs in sort of intermediate mass stars. All right. So they're all high mass stars technically, but the neutron star is sort of the middle thing that happens. And the neutron stars are the result of the smallest high mass star supernovas. So we can see this as a much more violent explosion. So we saw that a neutron star is the ball of neutrons left behind after the massive star supernova, which we talked about in the last chapter. Now the neutrons just have a different degeneracy structure than electrons. Their energy levels can be more compact and closer together. So degeneracy pressure of neutrons still supports them against gravity. It's just a different layout of energy levels. Basically, it's like this. What I mean by that is, so you have the, let me do another color. Basically, if you look at an electron's levels, it might be something like this, right? Whereas the neutron star, the same 4 levels are going to be packly, oh, wait a minute. The layers are going to be more tightly packed together. All right, and they'll have a different distribution. So in the same sort of energy space, you'll be able to fit a lot more neutrons, and that will make them correspondingly smaller. So if you remember, the white dwarf could be the size of Earth and have a whole solar mass of mass, right? Which can seem pretty impressive. We just talked about this slide, so I'm not going to redo it. However, a neutron star is about the size of a small city. All right? So neutron stars are the densest objects that can be described with physics, because black holes, like I said, we're limited there. But neutron stars are among the densest objects in the universe. If you were to take a small little teaspoon of neutron star, it would very likely have much more mass than Mount Everest. Just a small, tiny little bit. So as you can imagine, neutron stars usually have a mass greater than 1.4 solar masses. So we're talking 2 to 3 solar masses, and they are only the size of, say, Manhattan if it were a sphere. So much smaller even than the Earth. Okay, so very compact, very, very dense. Now, neutron stars were actually discovered because they rotate very quickly. And they were, you could see these very quick pulses emanating from a very small localized area in space. And I want you to notice how far apart these pulses are. They repeat at a precisely, and these are measured, 1.337301 seconds. So a very specific interval, all right? And that's indicative of the rapid rotation rate of the neutron star. So neutron stars frequently we talk about years, like, it takes, or short days. So it takes the Earth 24 hours to rotate once, right? Whereas a neutron star may rotate dozens of times in 1 second, if you want to get dizzy. So you'll notice, though, the dates, though. So using a radio telescope in 1967, Jocelyn Bell noticed very regular pulses of radio emission coming from a single part in the sky. The pulses were coming from a spinning neutron star, a pulsar. So the discovery of neutron stars is this is a discovery in 1967. All right. So I mean, that was only about 13 or 14 years before I existed. And students tell me I'm not that old. So if I'm not that old, neutron stars aren't that old. All right? And we're getting very clear in talking about stellar properties and what we know about stars. We're kind of getting in. We started with Galileo and simple stuff we could see, but you're noticing we're getting very modern very quickly. We're in the good old 20th century. So the pulsar at the center of the Crab Nebula pulses 30 times per second. That means it rotates essentially 30 times every second. So, you know, that would be dizzying to be on. Plus, you know, the mass would just crush you. I think we can see it here in the Crab Nebula in X-rays and visible light. Okay, we can see that. Now, with pulsars, you'll notice that the beamed radiation aligns with the magnetic field of the neutron star, not necessarily the axis of rotation. Okay, so it can make it seem like, oh, well, this must be where it's rotating, but this is actually why you can see it, right? So the magnetic field will precess and move around, driving these beamed radiation particles out, and then, but it'll be off axis, so it'll just kind of go around and around like a top. These actually sort of behave like lighthouses. I think that's what the next slide shows. That these pulsars are like cosmic lighthouses. I don't know where they're pointing the way to, but that's what we can see. So why must pulsars be neutron stars? Well, the circumference of a neutron star is around, remember, this is pi, so we can write that as all circumferences are 2 pi r. So the circumference is about 60 kilometers, right? So the spin rate of fast pulsars is 1,000 cycles per second. That's got to be rough. The surface velocity is around 60,000 kilometers per second, or 20% the speed of light. So escape velocity from a neutron star is going to be comparable to the speed of light. So basically, neutrons are the only, we can simulate these with neutrons, and a neutron will hold. We can model it with the quantum physics of neutrons and subject them to these conditions, and the neutron star holds. Literally anything else you can think of will be torn to pieces. Couldn't survive it. So neutrons are the simplest explanation. They fit within our models, so that's why pulsars are deemed neutron stars. The whole process behind it is we see this object that has this heavy mass, right? So we can measure the mass, and we can measure how fast it's spinning. All right, and then once we do that, we can sort of localize how big the object must be. So we have a heavy, super compact object, and then you start saying, well, is it possible, what in known physics can behave under such conditions? And well, we have neutrons. When we get to black holes, the answer is nothing, which is why they're black holes. You know, when we do the same thing for more massive stars, we just get a question mark, because there is nothing that does that. And that's when you have a black hole instead of a neutron star. Instead of neutron star. Okay. So let's see. Oh, we already see that stuff. Okay. So in a neutron star, in a tight binary system, again, these things don't, I think what ends up happening with a neutron star when it's inert is that, again, you can have neutron star binaries, neutron star white dwarf, neutron star black hole. You can have all sorts of binaries. But in the neutron star binary, you can get these intense X-ray bursts, all right? Where in the scope of seconds, you can just sort of get these large shots of very fast X-rays. And so matter falling towards the neutron star can form an accretion disk, just like a white dwarf binary. And accreting matter adds angular momentum to the neutron star, increasing its spin. And episodes of fusion will blast those X-rays to the surface. Now, I don't think you can ever add so much. I believe the mass required to add a neutron star past the neutron star limit would indicate other things happening. You'd probably at that point have dual neutron stars or dual supernova explosions, things like that. So I don't think it can quite vaporize like the white dwarf does, or at least I've never read anything about it. So we can see here the summary of what happens to X-rays or X-ray bursts. Now, neutron star mergers gave us some of our first indirect proof of gravitational waves. All right. So two neutron stars in a close orbit, we can actually directly measure the gravitational waves as they spiral together, and the figure shows the observation for one of these systems. So this is an indirect observation of the gravity waves, right? So you look at the observed data point of where the deviation from its 1974 orbit, and you can see that by the end of 2005, you have very good data that strongly supports gravitational waves, but it's the effect of the gravitational wave, it's not the direct measurement of the gravitational wave. And in 2015 was the first time we did direct measurements of gravitational waves. It was the first time they were seen. So now the neutron star still has the same quantum limit, right? And that's our Heisenberg uncertainty principle. We'll write it again. Right? So as delta x goes down, delta p must go up, and the neutron star degeneracy pressure can no longer support a neutron star against gravity if the mass is equal to 3 solar masses or above. So one would hope that because we don't know of anything that can, no other state of matter, if you will, that we should never find compact dead objects with mass greater than 3 solar masses. But we do. All right? We discover black holes. So black holes are something that take a while, like I said. So what I'm going to do is, instead of going over, I'm going to show you the first slide of black holes, and you're going to see why it's unsatisfactory. You waited all this time to get to black holes, and we're finally going to talk about them. And you'll notice the first thing you see is this thing, where it says the curvature of space-time becomes greater and greater as we approach a black hole, and the black hole itself is a bottomless pit in space-time. So in order to understand black holes, we have to understand what space-time is, but this is all either of your books says about it. They don't go into space-time because space-time can be difficult. So what we're going to do is I'm going to put together the lecture for next time, and I'll expect you to watch 3 videos before next week. So I'll post those tonight, and then during our break you'll watch the other 2 videos, and so we'll probably spend the first hour talking about those videos, or we may even just meet briefly and do it, because but there'll be a lot of stuff. Yeah, so usually when I teach this in class, and I'm going to stop recording, so this is black holes, so that'll be the end of part 2.